Have you ever wondered why the most advanced aircraft in the world are still assembled with millions of rivets? Welding has long been an industrial standard, but in aviation it is used very sparingly. The reason is not industry conservatism but physics, materials, and operational requirements. Welding is a method of joining metals in which edges are locally heated, partially melted, and form a single seam. In mechanical engineering this is convenient and technological, but an airplane is a fundamentally different environment. Cyclic loads, pressure changes, constant vibrations, and extremely strict requirements for every component all act here. First, metal fatigue and the behavior of a weld under cyclic loads. An airplane undergoes tens of thousands of cycles over its service life. Takeoff, climb. These are repeated loadings during which the fatigue is one of the main factors in the failure of aeronautical structures. A weld is a zone of local high-temperature exposure where the metal has been heated and cooled. A heat-affected zone and residual stresses form around the seam. Depending on the alloy and the technology, welding can reduce fatigue strength compared to the base metal. For thin-walled skins, where the skin often has a thickness of only a few millimeters, such effects are especially dangerous. Welded joints in fatigue regimes demonstrate more complex and less predictable behavior than riveted or bolted joints. Second, structural reliability of load distribution. A riveted joint consists of many separate fastening points. The load is distributed along this line. If degradation and is detected during scheduled inspections, a defect in a weld can lead to less predictable crack propagation. Third, materials. Aviation uses aluminum alloys, titanium, steel, and composites, and not all of these weld the same way. Aluminum alloys are more difficult to weld than steel. Many high-strength aerospace aluminums are sensitive to thermal exposure, and without special technologies welding can noticeably reduce strength and fatigue characteristics in the weld zone. Composites, in the classical sense, are not welded at all. Adhesives, mechanical fastenings, and integral panels are used for them. Dissimilar materials, for example metal and composite, are more rationally joined with fasteners and adhesives because of differences in thermal and mechanical properties. This makes rivets, bolts, a universal solution for complex and mixed construction of deformation and reparability. The skin and structural elements of an aircraft often have a thickness of only a few millimeters. Welding in such conditions leads to local overheating, warping, deterioration of geometry, and the development of residual stresses. Even a small deformation of the shell worsens aerodynamics, complicates assembly, and increases the risk of fatigue damage. A riveted joint allows assembly without significant thermal exposure to the material and provides ease of repair. A rivet is easier to remove locally, a panel can be replaced, and restorative work can be performed in the field according to approved documentation. Now about rivets and the inspection process. Different rivets are the basis of structural. Blind rivets are used where there is no access to the far side, and they are applied strictly according to certified requirements. In addition to rivets, bolts and specialized systems such as high lock and lock bolt are widely used. Installing a rivet is a complex operation. The hole is prepared to precise tolerances, the rivet is set, and the second head is formed. After that the joint undergoes inspection. In aviation, inspection is not done by eye but by measurements, tolerances, controlled torque moments, assessment of fit tightness, and, if necessary, non-destructive inspection methods. Practice and history are important too. In the mid-20th century,